So from the previous lecture, we had a system of equation which was x minus y equals to 3, x plus y equals to 7, and we wanted to use the row reduction operation to find the solution set to that system. And so what we need to do is to put the system into what we call an augmented matrix form. An augmented matrix form is a matrix together with a vector where the matrix is the coefficient of the matrix of the equations, and then the vector are the numbers or the integers after the equality sign. So we pick out the coefficient of our system. The coefficient of x in here is 1. The coefficient of y in equation 1 is -1. The coefficient of x in equation 2 is 1. The coefficient of y in equation 2 is 1. And then we form an augmented form with that system. So augmented with 3, 7. Alright. So the next thing that we need to do is to either add, subtract, add, multiply any of these rows so that we can achieve an echelon form, or reduce this matrix into an echelon form. An echelon form is if you have a matrix like 1, 1, 4, 7, then an echelon form is simply an upper triangular matrix, or reducing this matrix into an upper triangular matrix. So we have 1, 1, 7, and then we have 0 here. So we form what we call an upper triangular matrix. That is all the components, including those on the leading diagonal, are integer values, aside 0. Some could be 0. And then all the integer values below the leading diagonal are all zeros. This is what we call an upper triangular matrix. So back to what we're doing. If we have a matrix augmented with a vector form, then we need to reduce this matrix into an upper triangular matrix. So what do we need to do so that we can change the 1 over here to 0? Now we have a 1 and then we have a 1. Then if I multiply this row by -1, then I'll have -1 here. If I add -1 to +1, I'll get 0. So the first operation that I'll perform is to multiply my second row by -1 and then add it to row 1. So I have row 1, I have row 2. So first operation is -1 times R2, and then I add it to row 1. So this will give me, mind you, we're not doing anything to row 1. It's only row 2 that we're performing this operation on. So I maintain my row 1, which is 1, -1, and then my 3. So -1 times 1, which is -1, plus 1 will give me 0. -1 times 1, which is -1, plus -1 is -2. -1 times 7 will give me -7, plus 3 will give me -4. And so we've been able to reduce our matrix into an upper triangular matrix. All the components below the leading diagonal are zeros. And so we can transform our matrix back into a system form. So we pick row 1 multiplied by xy, therefore we have x minus y, and this is equals to 3. We have 0 times x minus 2y, and this is equals to -4. So let's label these equations, say 1 and 2. So from equation 2, I have -2y is equals to -4. Therefore, my y is equal to 2. Now, if I substitute this value into equation 1, I'll have x minus 2 equals to 3. So x is equals to 3 plus 2, which is equal to 5. Therefore, using the row reduction approach, our solution set is x equals to 5, y is equal to 2. Now, using the graphical approach, what I'll do is to label my axis. This is my x, this is my y. The equations are x plus y equals to 7, x minus y equals to 3. So you plot the graph for x plus y, which will be that way. Then you plot the graph of x minus y, which will be this way. So the solution set using the graphical method is where both lines intersect. So any point over here cannot be a solution to this system. A point over here can also not be a solution to this system. The only solution to this system is where both lines intersect. So on the x-axis intersects at 5, on the y-axis intersects at 2. Therefore, this is my solution. Therefore, the solution set to this system is when x equals to 5 and y equals to 2.